High-temperature oxidation, processes affecting materials under extreme heat conditions. Overview and definition to high-temperature oxidation. High-temperature oxidation is a critical form of corrosion that occurs when metals react with oxygen at elevated temperatures, typically starting around 900 degrees Fahrenheit or 482 degrees Celsius. This process leads to the formation of oxide scales on the metal surface, which can either protect the underlying material or accelerate degradation depending on their properties. Protective oxides such as alumina, Al2O3, chromia, Cr2O3, and silica, CO2, form dense, adherent layers that slow further oxidation. In contrast, non-protective oxides like iron oxide, FeO, and nickel oxide, NeO, tend to spall or crack, exposing fresh metal and increasing corrosion rates. High-temperature oxidation is particularly relevant in industries such as aerospace, power generation, and nuclear energy, where components operate under extreme thermal conditions. Understanding this phenomenon is essential for designing alloys and coatings that can withstand prolonged exposure to oxidizing environments without compromising structural integrity. Key aspects of high-temperature oxidation: protective versus non-protective scales. The nature of oxide scales formed during high-temperature oxidation determines whether the process is controlled or catastrophic. Protective scales, such as Al2O3, Cr2O3, and CO2, create a dense barrier that limits oxygen diffusion and slows corrosion. These oxides grow slowly and adhere well to the substrate, making them ideal for high-performance applications. Non-protective scales, including FeO and NeO, are porous and prone to spalling, which exposes fresh metal to oxygen and accelerates oxidation. The formation of protective oxides depends on alloy composition, particularly the presence of aluminum, chromium, and silicon. These elements are deliberately added to steels and superalloys to enhance oxidation resistance. Understanding the distinction between protective and non-protective scales is crucial for material selection and design in high-temperature environments. Applications and challenges: industrial relevance. High-temperature oxidation is a major concern in industries where components are exposed to extreme heat and oxidizing atmospheres. In aerospace, superalloys used in jet engines must resist oxidation at temperatures exceeding 1000 degrees Celsius to maintain performance and safety. Power plants rely on stainless steels and coated components to withstand oxidation in boilers and turbines operating under high thermal loads. Nuclear reactors present unique challenges, as zirconium alloys used for fuel cladding can oxidize rapidly in high-temperature steam, especially during accident conditions, leading to hydrogen generation and safety risks. These applications demand advanced materials and coatings that can form stable, protective oxide layers under severe conditions. Failure to manage oxidation can result in catastrophic equipment failure, costly downtime, and safety hazards. Factors influencing oxidation: temperature, alloy composition, and atmosphere. Several factors govern the rate and severity of high-temperature oxidation. Temperature is the most critical variable. Oxidation accelerates exponentially with increasing temperature and prolonged exposure. Alloy composition plays a vital role, as elements like aluminum, chromium, titanium, and silicon promote the formation of protective oxides. Microstructural characteristics, such as grain size and porosity, also influence oxidation resistance, with finer grains often providing better performance. The surrounding atmosphere can exacerbate oxidation, particularly when water vapor or sulfur compounds are present, as these species disrupt protective oxide layers and increase corrosion rates. Understanding these factors enables engineers to predict oxidation behavior and implement strategies to mitigate its effects. Mitigation strategies: alloy design and protective coatings. Mitigating high-temperature oxidation involves a combination of material design and surface protection techniques. Alloy development focuses on incorporating elements like aluminum and chromium to form stable, protective oxides such as Al2O3 and Cr2O3. Advanced superalloys used in aerospace and energy sectors often contain complex mixtures of these elements to optimize performance. Protective coatings, including aluminide and silicide layers, are applied to critical components to enhance oxidation resistance. Modern surface treatments, such as plasma electrolytic oxidation, create ceramic layers like zirconia, 02, that provide exceptional thermal stability. These strategies are complemented by operational controls, such as limiting exposure time and managing environmental conditions, to prolong component life and ensure reliability in high-temperature applications. Summary and key takeaways: Importance of managing high-temperature oxidation. High-temperature oxidation is a complex phenomenon that poses significant challenges in industries operating under extreme thermal conditions. Its impact on material integrity and system reliability necessitates a deep understanding of oxide formation, alloy behavior, and environmental influences. Protective oxides like Al2O3 and Cr2O3 are essential for controlling oxidation, while non-protective scales accelerate degradation. Effective mitigation strategies include alloy design, application of advanced coatings, and surface treatments. By implementing these measures, engineers can enhance component durability, reduce maintenance costs, and ensure safety in critical applications such as aerospace, power generation, and nuclear energy. Continuous research and innovation in materials science remain vital for addressing the evolving demands of high-temperature environments.